Okay, so let's start by reviewing what a buffer is. So if we go to our ideal amplifier model, you see our amplifier has an Rin, it has a voltage gain, and it has an R out. Now when we take our amplifier and we apply our source, the source has some series resistance, which is called RS, and we're usually driving a load, which is RL. And this is RV out. And so what you see here is we get loading here, which is RL over RL plus R out. So if R out is much, much less than RL, then this whole term is equal to 1. And then we also have input side loading. And then this has Rin over Rin plus RS. And this is also equal to 1 if Rin is much, much greater than RS. So you see, we want to create a buffer that has a small R out and a large R in. And that's called a buffer. So the buffer that we're going to be doing is a common collector. And we are designing it to have an input impedance greater than 20 kiloohms and an output impedance of around 100 ohms. Okay, so let's go through our design process. So let's look at some possible steps for our design process. So the first step is get the basic circuit. And then 2, from the basic circuit, we want to get the pertinent equations. And then we want to come up with the most important design. So we're going to do an AC design. And then we usually go and do the DC biasing to get it to be at the right design point. Okay, so let's start with our basic circuit. So we're going to start with a common collector. So we're just going to go to our BJT equation sheet, and we are going to look for our common collector amplifier. So the common collector has the input into the base and the output here. So that is our basic design. So let's copy this over. Looks right here. Okay, now we have to add a little bit to this because we have to have some biasing. So we're going to have to add in some biasing resistors to get it to work out, and we want to make sure that we include those in our design. Okay, and then here is our input, here's our voltage equation here. Okay, now we also want to look at what our output and input impedances are. So you see my input is looking into the base with an emitter resistor. So we go and look at that. So this is the piece that we have right here. So you see this is our input impedance. Okay, our output is looking into the collector. So let's go take a look at that. So then we're looking into the collector. So we have this case right here. So we're going to grab that one. And we're looking in here. But what we see here is that we also have an emitter resistor. So we know that we have 1 over GM looking up. We also need to figure out what is the Thevenin equivalent looking down, which is RE. Okay, so let's go now, and we have our basic design. Let's look at our pertinent equations. Okay, so we have this equation right here, which is our voltage gain equation. Okay, we also have our input equation, Rin, which is right here, which is R pi plus beta plus 1 times Re. And then we have our output impedance here, and so it's 1 over GM looking up and Re looking down. So our R out is going to be that parallel combination. Okay, so what we have to do is we have to pick which of these is the most pertinent. Now, typically in a buffer circuit, we don't really worry about the voltage gain. If I look right here, you see our voltage gain is going to be less than 1. So it doesn't really have any gain. The goal of a buffer is to balance out your input impedance and your output impedance. So what we're going to do typically on a buffer, lots of times the output impedance is the dominant case. So we're going to start with that one as our dominant equation. So we're going to set that equal to 100 ohms. Okay, now we have 2 variables here, and we are going to try and make it such that Re is much, much greater than 1 over GM, such that we only have to worry about the 1 over GM. And then we have to come back and check it to make sure that it works. So we have 100 is equal to 1 over GM, which is going to be equal to VT over IC, which is 0.026 over IC. So this means that my IC so in that case, my IC is going to be equal to 0.26 milliamps. Okay, so now that we have this here, we're going to come in here and we're going to check and make sure the Re is large, and then the bigger the Re, the bigger my Rin is. So let's look at my Rin. What is my R pi? So my R pi, just to check everything out, is going to be equal to 0.026 divided by IB, which is going to be equal to beta times 0.026 over my IC, which is equal to 300 times 0.026 divided by 0.26 times 10 to the minus 3. It's kind of odd that they're both 0.026, but that's just how it works. And so that works out that my R pi is equal to 30 kilo ohms. And you see that is already larger than our 20 kilo ohm that we need. So we're doing really good because you can see that it's just going to be a lot bigger than the 30 kilo ohms when I add in my RE. Okay, so we're done with our basic, and now what we want to do is now we want to come in here and we want to do our look at our DC equations. Okay, so we want to get the maximum headroom. So you see with our output, where's our basic circuit? Okay, with our output here, we want it to look at where do I want to set it. So it can go down to 0 before it clips, and it can go up to about VCC because we can get about 0.2 volts across here. So the maximum is when it hits saturation, and the minimum is where it hits cutoff, which is a little different than our common emitter amplifier. So we want to set our output basically right in the middle. So we want V out DC to be equal to about 5 volts, which is going to be equal to RE times IE. So we have 5 equals RE times beta plus 1 over beta times my IC, which is basically RE times 0.26 times 10 to the minus 3, which means my RE is equal to, so the RE is equal to 19 kilo ohms. So then, just to check it, my Rn is going to be equal to 30 kilo ohms times 19 kilo ohms, whoops, plus, which is definitely much, much greater than 20 kilo ohms. So we have a really large input impedance. Okay. So now, and then we see that our input impedance also has an R1 and R2. So just like we did before, we have an input impedance seen looking in this way, in parallel with one looking this way, in parallel with one looking that way. So what we see that our actual Rn is going to be equal to R pi plus beta plus 1 times Re in parallel with R1 in parallel with R2. And we want to make sure that that's much, much greater, or that that's greater than 20 kilo ohms. And so that means that we want to make sure that R1 in parallel with R2 is greater than 20 kilo ohms. So we want to pick an R1 and R2 that are fairly large, but we don't want to get up into the mega ohms because then everything gets too bad. Okay, so now that we have all this basic stuff, let's kind of write down what we have. So we want RE equal to 19 kilo ohms. We want IC to be equal to 0.26 milliamps. Okay, and then we want R1 and R2 both greater than 20 kilo ohms. So now we're ready to go to LTSpice to do our biasing. Okay, so here's LTSpice. So we're going to start by grabbing a BJT, which is an NPN. Right click, and this is a 2N3904. We want a resistor down here. We want our 2 biasing resistors. Okay, we want to set this at 19 kilo ohms. we got to add in our voltage source. And that was 10 volts. Let's just call it VDC. Give it a ground. Let's move these around, make it a little prettier. And then we're going to do this DC analysis part first before we come in and add in our AC source to check everything. So let's call this RE and call this R1 and this R2. Now we want these to be large, so let's just pick one. You know, we want to make sure that everything is smaller than a mega ohm, but you might as well have it as big as possible. So we're going to put in 1 meg, and we are going to sweep this one. Okay, so then we type edit spice directive, and then we're going to go dot step param. So we're going to step a parameter. We're going to change R, and we want to change it. Let's go 100K to 1 meg, which is 1000K, and we'll just do it in 10K steps right now. Okay, so then we want to do simulate a DC operating point. And let's add in our output. Just call it out, and it goes down here. Okay, and then we sweep this. And we want to have 5 volts. You see it doesn't quite get there when it hits 1 meg. So what we're going to do is we're going to call this one R1 meg and change this one to RR and then sweep it. Okay, and then we want this to be about 5 volts. So 681, let's just swing this a little bit smaller. Let's go from 500K to 600K in 1K steps, just to get a little better resolution. Oops, a little bit. We need a little bit bigger. So we're going to go from 600K to 700K. Okay, that's better. So then we want about 5 volts. Well, really, we want to make sure that our collector current is right. Let's look at our collector current. And we wanted 0.26. So it all works out about the same. So we want 690K. So if I make this 690K and that one 1 meg, we can get rid of our step parameter and rerun this. And we see here's our collector current 0.26. Here's our V out, really close to 5, and then everything looks good. Okay, so now we want to add in our voltage source. So we are just going to copy this one. And we're going to make this a sine wave, 0 DC, an amplitude of 2 volts. If I remember what we want to put in 2 volts. Now at first we're not going to put an input and output resistance, and we'll do 1 kilohertz. And we need a capacitor. Okay, so what value do we want this capacitor to be? So we want, if we're doing 1 kilohertz, we want to set this as at like 100 hertz or 10 hertz even. So let's come in here, and we remember that my cutoff frequency is 1 over 2 pi RC, which is equal to, let's just set it at 10 hertz. We got lots of room. Okay, so what is my resistance? Okay, so we can see that the looking in this direction was really, really large, and looking in this direction, well, right now it's just 0 because I don't have anything here, so it's going to be a really big number. And so we can see that my input impedance was 1 meg in parallel with 690K in parallel with 30K plus 19K times 301. So this is equal to 1 mega ohm in parallel with 690K in parallel with, and this is in parallel with 5.7 mega ohms. So this whole thing is equal to, so this is equal to 381 kilo ohms. So you see we're going to make this 381 times 10 to the third times C. And then we're just solving for RC. So we get C is equal to 42 nanofarads. So we'll just come over here. We want to set that corner just down there somewhere. So we're just going to make this 100 nanofarads. And let's run this and see what we have. So we're going to change this to a transient. We run this. So here is our 2 volts amplitude, 4 volts peak to peak. And we look right here, and we have so we have 3.97 volts, so that's pretty good. Okay, so now we want to check and make sure that our input and output impedances are good. So we're going to come in here, and we're going to make this our 20 kilo ohms, run this, and then we want to look at how does this voltage here compare to the voltage there. So you can kind of see that we have very little loading because we have really good, very little drop there, so that all works well. And then we wanted to make sure that our output impedance is okay. So right here, you see this is well, now it's about 3.77. And we're going to add in a resistor here. That's our 100 ohms. Let's move this over a little bit. Now we have to add in, okay, so if I just put this right here and make this 100 ohms and run this, well, you see everything got messed up, right? And the reason that everything got messed up is that for my DC analysis, I needed 19 kilo ohms. Well, I put this in parallel. When I put this in parallel, it messed everything up. So I need to make sure that that this doesn't affect my DC and only affects my AC. Otherwise, my bias point gets all messed up. Okay, because my bias point here looks like it's about 0.7 volts. So we need to figure out what is the resistance that this one sees. So this one's going to see the 100 ohms plus the 19 kilo ohm. So I find my Thevenin equivalent in this case, and it comes out to about 0.8 microfarads. So we're just going to make this one kind of 1 microfarad and see how that works. And so we run this, and you can see with this capacitor in, we still have kind of a DC level that's in the 5 volt range, which is about where I wanted my DC point to work. But you can kind of see that it's kind of clipping down here. Let's make this a little bit bigger as we try and figure out what's going on. So you see as this is bigger, it, and as I go bigger and bigger, right, then you see that it's starting to clip on the bottom. Let's go back to our 1K. So what you see here is that the top looks good, but the bottom is clipping. And what is this? This is at about 5 volts, so 5.3 volts, it's clipping. So why in the heck is it clipping? Well, let's go and look at the voltage, right? So is this point, really we want to look over at this point rather than this one, because you can see that this one takes out the DC level. So let's go back to this side. So in saturation, we can only have 0.2 volts across here. So is this within 0.2 volts of 10? No, we're only at 7. That's good. And then does this point approach ground? No, everything looks good. So it's not a voltage clipping problem. So we got to figure out what's going on. Well, okay, so let's look at current. Okay, so let me move this down a little bit so it's easier to see. Okay, so we're worried down in here. So let's look at the current. So in AC, you see that, let's look up here. Okay, so if I look right here, you can kind of see where it starts to clip, and this is clipping when the current is basically goes to 0. So let me put in an imaginary resistor just so I can see direction. The problem is sometimes you can't tell which direction things are flowing. So we're going to make this 1 nano ohm. So it's basically not even there. But then if I do that, you can see I can make sure that my current's flowing down. Okay. So at this point, I have current flowing down the transistor. But then if I were to keep this going around, so if I were to keep extending this, then that means that my current goes negative, which means that the current's trying to flow up. And if the current tries to flow up, well, this BJT only lets current flow down because of these diodes that are built into its response. So when the current is trying to flow up, then it stops working. And so what we see here is that this current, the AC part, has to be equal to this one plus that one, right? And so once this resistance gets too small, it's trying to pull too much current. So we need to set my bias current point, to be not a milliamp. We need to set it higher so that it can handle this. Okay, so let's go back and look at what we're doing. Okay, so we need more IC bias, or the DC value, right? So we're trying to get a V out that's equal to 2 volts and we want an R out that's equal to 100 ohms. That means that my I out is going to be equal to 2 over 100, which is equal to 20 milliamps. So if I need an output current of 20 milliamps, I need to set my bias current to be larger than that. So I have to come in here and set IC. Let's just set it to 30 milliamps to make everything work out. Okay? And then this means what? So this means that I want REIC still to be centered at my 5 volts. So that means I have RE times 30 times 10 to the minus 3 is equal to 5. So I need RE equal to 167 ohms. Okay, so but now we got to go back and check everything to make sure everything is still working. So now we have an R out was equal to 1 over GM in parallel with RE. So my 1 over GM is equal to 0.026, which is my VT, divided by my IC, which is, well, let's just make this into millivolts. So this is 26 millivolts, and we have 30 milliamps. So my 1 over GM, so this is equal to 0.87. So this is still much, much less than my RE, which is 167. So now my R out is equal to 0.87 ohms. So you see, I still have a small output impedance. Okay, and my input impedance should stay around the same point, except for now I have to rebias. Okay, so let's go back and check my R in. So now my R in is going to be equal to R pi plus beta plus 1 times RE. Okay, so this is going to be equal to 300 times 0.026 over my current, which is 30 times 10 to the minus 3. That's my R pi. Plus, I have a 301 times 167. So this is equal to 300 times 26 millivolts divided by 30 milliamps. So this is 260. And this one is 301 times 167. And then this is 50 kilo ohms. So now you see that my input impedance went down a bunch because I'm driving more current, but it still works out because it's still greater than 20 kilo ohms, so we're still okay. So now we're going to go back to LTSpice. Now we have to come back here. We're going to, let's go back to our DC analysis like we were doing before. Except for now we're going to set this to 167. We don't need any of this yet. Okay, and then we're going to go back and redo our DC analysis. So we are going to go dot step param. We're varying our resistance. And then again, we're going to go from 100K to 1000K in 10K steps. Let's go back to our DC operating point 1. And we were changing this one to our R. Okay, so we run this. and we went too high, so now we're going to do and swap them back again. Change this one to R. Okay, so we set this bottom one to 1 meg, and we're sweeping this, and then we had to come down farther, so we're going down to 10K, and we want the 5 volt swing. So it's about 38K. So we have a lot less input impedance because we're driving heavier currents. So, but still, this is bigger than my 20 kilo ohms, so we're still within the necessary spec that we needed. So this is about 38K. So let's come in here and change this from like 20 to 50 to get a little bit better resolution. Okay, and we wanted 5 volts. So about 39K, about the same. So we're going to go 39K, get rid of this, rerun it, and you see that we have a V out of 5 volts and an IC of about my 30 milliamps. Okay, so now we're going to come in here and add back in our input. So we're going to add our capacitor. We're going to add our voltage source. Let's see, we wanted a 20 kilo ohm here. But now this is 20 kilo ohms, and this one was about 50 kilo ohms. So we need to recalculate what. So we need to change what our capacitor is, and now we need about 0.3 microfarads. So our capacitor had to get a little bit bigger. Let's go 1 micro here. Okay, so let's run this first, see how, oops, this is a DC. We want to change this into our sine wave. And we want to switch back to our transient. Okay, so check everything here. So this is our 4 volts. You can see that now we have a little bit of loading. So this is 2 volts. And the blue one is 1 volt. So you see that we've dropped in half. So our output and our input impedance is about the 20 kilo ohms now, but we're barely within spec. Okay, now we're going to add in our capacitor, add on our load resistor. This was our 100 ohms. And if I remember right, this was about 20 micro. And we look at our output, and now we're not clipping at the bottom because you see that now we're going down to about 18 milliamps, but we haven't gotten to where it starts to swing 0. So if we wanted to, you see now we can start increasing this. You know, it's starting to get a little lower. And then eventually this gets to go negative. But we have lots of bias current, so we can handle it now. And now you can see that it's starting to clip. So if we keep going up, eventually it'll clip because we run out of bias current. So now it clips once this current here goes to 0. So we got to make sure that I have enough current. But for our design, this is all that we need.